Lab 2 further helped us visualize and understand the interactions between charged objects. The main key difference between this lab and Lab 1 was that we treated the U-tape as a line charge rather than a point charge. In order to solve for the overall charge on one U-tape, we needed to analyze the net force on the object when the momentum of the tape was not changing. Some key assumptions we had to take note of while creating a computational model include that we had to ignore air resistance acting on the moving tape, assume that each U-tape had roughly the same charge, and that this charge is evenly distributed along the length of the tape. While I did use the same method from Lab 1 to create the U-tapes, I utilized wooden sticks rather than books to prop up my U-tape. This setup allowed me to interact the two U-tapes together without having my hands interfere nearly as much. Here are some key results from Lab 2. My tape length was 0.175 meters, and I found the separation distance to be 0.0165 meters. I had to manipulate the charge on the tape until the magnitude of the electric force acting on the top tape was equal to the magnitude of the gravitational force acting on the top tape. I found the charge on the tape to be 1.78 times 10 to the negative 8 coulombs. As you can see, the charge on the U-tape when treated as a line charge is considerably greater than the charge on the U-tape when treated as a point charge. Lab 2 was primarily focused on creating a computational model for finding the charge on the U-tape, which is treated as a line charge. And when I say line charge, I mean a line of uniformly charged point charges. I will now go through the key steps in my code. The first step after including constants and values such as tape length and separation distance was to implement the function for producing an electric field. This function creates a vector for the electric field at an observation location produced by a source charge. Later, I will call on this function produce the electric field vectors at each of the individual point charges. The next key step is to create the line charges for the top and bottom tape. This function creates a line of uniform point charges, each with a charge and mass. Since I produced 10 point charges, each point charge will have a charge of the total charge divided by 10 and a mass of the total mass divided by 10. I called on the line charge function to produce my top tape and bottom tape. The uniform point charges in the top tape will be represented by red spheres, while the uniform charges in the bottom tape will be represented by blue spheres. Both the tapes have a length corresponding to the tape length I used. The bottom tape is positioned at the origin, while the top tape has a y-coordinate value corresponding to the separation distance. The next step is to produce the electric field vectors at each point charge in the top tape. This portion of the code calls on the e-field function to produce an electric field vector at each of the point charges. The observation locations are the location of the point charges on the top tape, and the sources are the individual point charges on the bottom tape. This portion of the code produces a green vector at each point charge. The vectors for a specific point charge represents the sum of the electric fields acting on that specific point charge by each of the point charges on the bottom tape. The final step is to create the force vectors for the electric force and the gravitational force acting on the top tape. This portion of the code calculates the electric force on each point charge by multiplying the electric field acting on that point charge by that point charge's charge. These force values are summed together to produce a vector for the total electric force acting on the top tape. A gravitational force vector is produced by multiplying the mass of the top tape by the gravitational constant. This is the computational model produced by my code. The line charges for the top and bottom tapes are represented by the red and blue spheres respectively. The electric field at each point charge on the top tape are represented by the green arrows. The white arrow represents the electric force acting on the top tape, and the yellow arrow represents the gravitational force acting on the top tape. As you can see, these two arrows are of equal magnitude but in opposite direction. It is important to have correct scale factors for the electric field arrows and the force arrows. I attempted to solve for the charge on the tape by hand. I created an integral that calculated the sum of the electric fields acting on an individual point charge. I then multiplied this electric field value by the point charge's charge to produce the force on that charge. I repeated this process for every single point charge. I knew the sum of these forces should equal the magnitude of gravitational force. Using this in algebra, I solved for Q. I found Q to be 1.85 times 10 to the negative 8 coulombs, which is similar to the value produced by my computational model, but not close enough. There are likely errors with my integral and how I accounted for the differing radius vectors for each source charge. I believe this model produces a value for the charge on the U-tape closer to the real value because this model more accurately depicts the distribution of charge on the U-tape compared to Lab 1. The difference in results is likely due to the fact that the electric fields produced by the source charges have both an x and y component, not just solely a y component as in the case for a point charge. This is why Q is larger when the U-tape is treated as having a uniformly distributed charge.